if it's a single point charge, perhaps even if it has a constant velocity like so, some place over here is going to experience this particle's magnetic field. But let's just see if you can put a few of these pieces together yourself. If for just a moment I hearken back to the days of electric fields, I would be able to determine the electric field if I know this distance, right? Now, answer me this. If I move point P closer to charge Q, will that increase or decrease the strength of the electric field? Let me say it again, because I want to make sure everybody can answer this question. If I move point P closer to charge Q, will I experience an increase or a decrease in the electric field? All right. So consider position S. Position S is clearly going to experience a larger electric field. That electric field is going to be in a slightly different direction, but definitely much larger. I say slightly different direction because point P and point S aren't along a line that connects them to Q. So the direction of the electric field for S will be like that, and the direction for the electric field for P will be like that. Does that make sense so far? But as long as this arrangement stays, those electric fields will remain the same for all time. Good so far? Now, if I asked you to calculate the electric field, you would just need to know what those two separate distances are. And from there, you could calculate the size of that electric field. Here's why the magnetic field is different. And as you're taking your notes, please actually take them. Listening is nice, but actually take them. The electric field was static. Once established, you could easily figure out what the electric field was everywhere in the space around those particles because it remains constant. Take a minute, get something like that into your notes. Again, once the electric field is established, it's constant. Therefore, you know what the electric field is everywhere in that space. Now, getting rid of this for a moment and going back to considering point P, what's the magnetic field at point P right now? It's got to be 0. Charge Q isn't moving. Now here's the rub. The instant charge Q has a velocity, a magnetic field is created. Now, bear with me. Do you think the magnetic field strength is constant everywhere in space? Or do you think places closer to the charge experience larger magnetic fields and things further away from the charge experience less magnetic field? Which makes the most sense? All right, so we all probably agree that proximity has something to do with the strength of the magnetic field. All right, then here's the problem. Are particles moving? Which means that point P is not experiencing a constant magnetic field, but a magnetic field that is going to be changing all the time. Right? The particle's only here for an instant and is gone. and is moved over to here. Suggesting that whatever we calculate for the magnetic field at point P only existed at the instant the particle is at the first location and then is constantly changing. This is why Biot-Savart is usually not taught for point particles. Because generally, independent particles moving through space are creating a transcendental field. A field that is transient, existing only for a brief moment and then is gone. Because it moves away from that point. In fact, when we try to consider what the shape of this field looks like, consider we look at as the particle moves through space, it's creating a circular magnetic field around it. A magnetic field that's smaller ahead of it, again, proximity, and of course, smaller behind it. So as this particle moves, its magnetic field, again, is very transient, increasing in size as it reaches a point of closest approach, and then reducing in size as it leaves. There is one saving grace here, though, something that is not like electric fields, something that makes this, in some ways, much easier to deal with. If you're in this region of space as the particle passes, that entire region is going to see a magnetic field that's all in the same direction, even if it's all not the same strength. So a magnetic field is going to be increasing in size and then decreasing in size. It will always be downwards into the board here, or downwards into the page. While on the other side, the magnetic field over here, always out. So the one nice thing at least is that, one saving grace is that. But aside from that, and if you're not in the same plane as the motion of the particle, that's not going to be true. But it is a bit of a convenience. Now, to get an idea for what this law looks like and understand that you will not have to actually calculate using this rule, but I think it's impressive for you to be able to discuss it. The rule looks like this, and I'm going to be, I'll be clear with you, there's no other way to write this rule for me to be accurate, so I'll explain why it's written this way, but just so you know, it's not pretty. This is a Biot-Savart law for a point particle moving through space at a specific instant in time, dv. You integrate this based on how the velocity is changing. We won't have to do this, but this is what the rule looks like. Sometimes, just so you know, I'm not going to rewrite it. Sometimes it is rewritten, though, as dq v cross r. This is the way I would prefer to see it, but I've seen the law both ways. This one makes the most sense to me. It assumes like a bar of charge moving through space. So it allows me to integrate across the geometry of the charge. But sometimes it's written as dv, so you can express the geometry of your configuration in terms of dV. It doesn't really matter which one you choose. They are linked together, the charge and the velocity. There are features of this law, though, I want you to know. And if you want to make it simpler on yourself, for those of you who just simple minds, for a point charge, this is it. It's not an integral. For a point charge moving through space, this is what it is. So again, not an integral. You can just do it like that. Now, there's a lot of little pieces here, but first, I really do hope that you see the clear similarities. There's something incredibly elegant about this symmetry in space, which is why I really like to make sure you've seen Biot-Savart for a point charge, because it is elegant. I don't know why space works this way, and nobody really does, but it has to work this way. For whatever reason, this is how it has to work. But the fact that they're both inverse square laws, the fact that they both have some single solitary constant that's related to 4 pi, again, weird. You know, the fact that they both are vectors and they both fall off, you know, at the same rate. There's just some certain amount of elegance there. But the cross product with R does add an intriguing difference. If our point is here, and we wanted to figure out the direction of the magnetic field at point P, I don't want to draw an X there, I'd rather we just assume that point P is inside that box. Determining the direction of the magnetic field can be done using the cross product here. It's V cross R hat. If you don't remember, R hat is a vector that connects the charge to the place in space. It's a unit vector. So although I drew an arrow that's the entire length of R hat is in the direction of R. So I know it's tough, but it's velocity first. And then you move your middle finger to line up with R, and your thumb points in the direction of the magnetic field, which is into the board. Now, it shouldn't surprise you if you place your thumb in the direction of the velocity, your fingers curl in the direction of the magnetic field, the same way it would for a current carrying particle or a current carrying wire, which still puts us into the board. Remember, our goal is to ensure that all of our methods for calculating direction that involve the right-hand rule are consistent. And this too is consistent, so the magnetic field into the board over here. Now, like I said, Biot-Savart, great, but I want you to imagine what this really suggests. If you have all of that information, how fast it's going, how far away it is, and the size of the charge, you can get the magnetic field. It's not that hard to calculate, but it only exists at that moment for an instant. And then all of a sudden it's changed, its location. R is changing, and R, V cross R is never changing here, but R is changing all the time. We know that R is related to V. The only time it's not, and this should flip you out a little bit, if the velocity of the particle is that way, R is related to V in a very known way now, but there's no magnetic field. This particle, Q2, doesn't create a magnetic field in front of it or behind it. And neither of them do. Remember, the way this works is there has to be a cross-product solution. Right now, the angle between V and R is 0. No magnetic field. So particles coming at you don't cast a magnetic field ahead of themselves. They cast it to the side, but not ahead. So if it's going to pass near you, yes, there'll be a magnetic field. But if it's going to strike you, no magnetic field. I'm not sure if that matters. Really? Even the schools locks down once the middle schools all start up, sending our attendance in. It's kind of crazy. All right. Now let's get to the one that you do have to do. This one you have to know, and there's no easy way around this one. This one we're going to be using. In fact, I just was being nice to you. I showed you Ampere's law first. I did that because I hope you all realize Ampere's law to figure out the magnetic field around a current was really easy to use, wasn't it? You guys saw it yesterday. It was just stupid easy. Well, remember when we would do those rules with the when we'd find the electric field from a line of charge, just to realize that Gauss's law made it super easy? Well, we're doing it in the reverse. We know our answer is going to be that the magnetic field from a long line of current, a long cable of current, is going to be mu naught times I over 2 pi r. However, we can find this answer by using the current form of the Biot-Savart law. The current form of the Biot-Savart law has to be written as a differential, because although this cable might have a current passing through it, as you probably can guess, this piece of current right here contributes to a magnetic field over here, just like a single particle would. And this piece of current also contributes to a magnetic field right here. And this piece of current does. You see where this is going, right? That each piece of current along the length of this wire contributes its own amount to the magnetic field at point P. And all of them together combine to form the net magnetic field. So if I wanted to find the magnetic field of this piece of current, which I will call ds, because it's based on the length of the wire, then its contribution to the magnetic field, and this is not going to be a surprise, I dot ds cross r hat over r squared times mu naught over 4 pi. That's Biot-Savart for a current carrying wire. Yep.
So, correct me if I'm wrong, but the mu naught, isn't it just 4 pi times 10?
Yes, I know. I get the irony here. I get the irony, and you don't have to go into it. Yes, mu naught is 4 pi times 10 to the negative 7th. And yes, Biot-Savart divides away the 4 pi. Yes, you're right.
So it's just times 10.
And just sit back and be happy for a moment, because yeah, trust me. And when I say trust me, remember, epsilon naught and mu naught can both be written in terms of C. Wait, let that play in your head for just a minute, because for all the electric field stuff, it's 4 pi epsilon naught, which means every epsilon naught can be written as mu naught and C. So if you really want to have your head kind of have some issues, you're right, why? I can